What is quantum networking? Executive summary. Quantum networking uses quantum physics to move information with qubits. It creates secure communication through entanglement and quantum key distribution. It also supports advanced computing by linking quantum devices. Scientists build quantum repeaters and quantum memories to extend network range and stability. Quantum teleportation transfers states without moving matter. These systems may form a future quantum internet that works with classical networks. Quantum networking could transform communication, sensing, and computing across many fields. Article: Quantum networking uses the rules of quantum physics to move information between distant places. It sends quantum states instead of classical bits. A quantum state can exist in more than one condition at the same time, and we call this superposition. This feature gives quantum networks special abilities. Scientists believe these networks will support new forms of communication and computation. They also think quantum networks will protect information in new ways. Quantum networking uses particles like photons to carry quantum information. Photons travel well through fibers and open air, so they serve as common carriers. A single photon can hold a qubit, which is a quantum unit of information. A qubit can be 0, 1, or both values at once. This ability gives qubits more power than classical bits in some tasks. Quantum networks use qubits to perform secure communication and advanced computing. Quantum networking depends on a key idea called entanglement. Entanglement links two or more qubits in a shared state. Each qubit keeps a connection to the other, even if they move far apart. This link behaves in ways that classical physics cannot explain. When you measure one entangled qubit, the other qubit responds instantly. This reaction happens even across great distances. Scientists use this strange behavior to make new network systems. Quantum networks create entanglement between distant nodes. A node can be a quantum computer, a sensor, or a memory device. The network then manages the entanglement so that devices can work together. Entanglement lets nodes share information in secure and powerful ways. It also helps networks move quantum states without moving the physical particles. This process uses a method called quantum teleportation. Quantum teleportation does not move matter, but it moves information. It transfers the state of one qubit to another qubit in a distant location. It also uses classical communication as part of the process. The sender performs a measurement and sends classical data to the receiver. The receiver uses this data to change its qubit so that it matches the original state. This method protects the quantum state because no one can copy it. Copying a quantum state breaks a rule called the no-cloning theorem. Quantum networks face many challenges because quantum states break easily. Light can fade inside fibers, and photons can disappear. A lost photon destroys the quantum state and the message it carries. Researchers build devices called quantum repeaters to fix this problem. A quantum repeater strengthens entanglement across long distances. It divides a long channel into smaller links and creates entanglement in each link. The repeater then performs entanglement swapping to connect the links. This process builds one long entangled connection. Quantum memories support quantum repeaters. A quantum memory stores a quantum state without damaging it. The memory holds the state until the network is ready to use it. This ability lets the network create balanced links. It also helps the network manage delays and errors. Memory systems must operate with high precision. They must also protect states from heat, noise, and interference. Quantum networking offers major benefits for secure communication. One main method is quantum key distribution, QKD. QKD sends encryption keys using photons. If someone tries to read the photons, the measurement changes their states. The sender and receiver see these changes and know an attack happened. QKD creates keys that attackers cannot copy or view without detection. Banks, governments, and research labs Test QKD for secure links. Another benefit is distributed quantum computing. A single quantum computer may not have enough qubits to solve large problems. Quantum networking links smaller quantum systems into a larger structure. Each system performs part of a calculation. The network then combines the results. This process could solve big scientific and industrial problems. It may also support new kinds of simulations. Quantum networks can also create advanced sensor systems. A set of entangled sensors can measure signals more precisely than classical sensors. They can detect weak magnetic fields, small temperature changes, or slight shifts in position. These measurements support science, medicine, navigation, and environmental monitoring. Entangled sensors gain precision that classical systems cannot reach. Researchers are building the first stages of a quantum internet. A quantum internet will connect quantum devices across cities, countries, and continents. Early testbeds already exist in several regions. These testbeds link universities, labs, and technology centers. They use fibers beneath cities and free space links between buildings. Some tests use satellites to move entanglement between long distances. The quantum internet will not replace the classical internet. Instead, it will work beside it. Classical networks handle normal communication, and quantum networks handle tasks that need quantum states. Many quantum protocols still need classical channels. The two systems work together to support secure and advanced communication. Engineers must solve many problems before the quantum internet becomes common. They must build better quantum repeaters, longer-lasting quantum memories, and more stable photon sources. They also need strong network protocols that manage entanglement and errors. These protocols must handle noise, delays, and losses. They must also choose the best paths for quantum states. Researchers also study materials that can protect qubits from noise. Some systems use trapped ions, which float in vacuum chambers. Other systems use superconducting circuits that operate at very low temperatures. Some systems use color centers and diamonds that store photons. Scientists test each method to find the best tools for future networks. Quantum networking will support many new technologies. Secure voting systems may use quantum networks. Space missions may use quantum links between satellites. Cloud providers may offer quantum computing over quantum channels. These changes may transform science, business, and communication. Quantum networking still stands in early stages, but progress looks steady. Each year, researchers break new distance records for entanglement. They also improve the stability of photon sources and memories. These steps bring the world closer to a full quantum internet. Students and engineers from many fields now join this effort. They study physics, computing, engineering, and communication. Their work shapes the future of global information systems. Quantum networking will likely grow through teamwork and innovation. Many nations support research programs. Companies design new quantum devices and tools. Universities train new experts who can solve complex problems. This teamwork creates strong progress in the field. Quantum networks may one day support everyday tools and services. Their impact may reach homes, schools, hospitals, and businesses. Quantum networking uses the laws of nature to protect and share information. It builds powerful communication systems with features beyond classical limits. It supports science, security, and computing. It encourages new discoveries in physics and engineering. It may become one of the most important technologies in the coming decades. Quantum networks may shape the way people share information across the world.